So just overlapping half-filled regular atomic orbitals didn't quite work because the bond angle was wrong. We saw that with the H2S. And here we can look at it again with carbon and hydrogen. So here's the orbital diagram for carbon, and here's an orbital diagram for hydrogen. Hydrogen has a half-filled orbital. Carbon has two half-filled orbitals. And so we could imagine, here, make another hydrogen. So these two orbitals could overlap. Whoops, that's not what I meant to do. These two could overlap, and these two could overlap, right? Overlap of half-filled orbitals. And so that would predict, here's our half-filled orbital for the carbon overlapping with the hydrogen, and here's another half-filled p orbital overlapping with the hydrogen. This third one is not drawn because it's empty, okay? Well, you're asking hard questions. Hold that one till the end. So that would predict that we would have a compound CH2 with a bond angle of 90 degrees. But CH2 doesn't exist. The smallest carbon-hydrogen compound is methane, is CH4, and it has a bond angle of 109.5. Just overlapping regular atomic orbitals, standard atomic orbitals, doesn't work. So we need an additional concept, and that's hybridization. The orbitals in a molecule are not necessarily the same as the orbitals in an atom. So hybridization is a mathematical procedure in which standard atomic orbitals are combined to form hybrid orbitals. They correspond more closely to the actual distribution of electrons in molecules. They are still localized on atoms, but they have different shapes and energies than the standard s, p, d, and f atomic orbitals. The hybrid orbitals are going to minimize the energy of the molecule by maximizing the orbital overlap. They give a better overlap because the electron probability density is directed more towards a single lobe instead of being symmetrical around the atom. Hybridization does require energy, so it will only happen if there's a payback in lowering of energy forming the bond. So what we're going to do is we're going to focus on hybridization of interior atoms. We are going to assume that the terminal atoms are unhybridized. They do hybridize, but we can get away with just pretending they don't. So atoms that form more bonds are more likely to hybridize. And that's one of the reasons we can ignore the terminal atoms. So again, this is a bunch of stuff leading up to, hopefully, pictures that'll make more sense. The number of standard orbitals added together, hybridized, always equals the number of hybrid orbitals. So if you start out with one orbital on this, if you start out with two orbitals, you're going to end up with two orbitals. They're just going to have a different shape, different energy. But you can't create or destroy orbitals, so I guess we could say there's conservation of orbitals here. The particular combination of standard orbitals that hybridize determines the shape and the energy of the hybrid orbitals. And the particular hybridization is the one that occurs that yields the lowest overall energy. And these calculations are way beyond the scope of this class. So what we're going to do is we're going to use Vesper theory. We're going to use Vesper theory to predict the hybridization. And that works for everything we need to do. Okay, so how does this work? Well, let's look at that carbon-hydrogen problem. Here we have an energy diagram for the valence electrons of carbon. Here's an s orbital, and it has a pair of electrons in it. The p orbitals are a bit higher in energy. This one's half-filled, this one's half-filled, and this one is empty. In hybridization, we can take all four of these orbitals and combine them together. So we take all four of these, combine them together, and then we're going to get four degenerate orbitals. They're all going to have the same energy. These will be higher in energy than the S and lower in energy than the P. This requires energy to happen, and so it just doesn't happen in the atom by itself. It only happens if doing this gives us a bond that releases energy. So here's the hotel analogy. So we're looking at the second floor of this hotel, right? So on the first floor, second floor. So here's the S room, here's the P room with 3 beds. What we're going to do here in hybridizing these is we're remodeling the rooms. So instead of having 2 different rooms, we're going to combine this into one room, and it's going to have 4 beds. So I took the S room and the P room, broke down the wall in between. That requires an investment, right? You have to get guys to come and do that. And it requires an investment. We're only going to do that if we're going to get a payback later. But I can hybridize these. And now what I'm going to charge for these beds is a little less than the P beds, the P orbitals, but more than the S. It's in between. Everybody okay? We're doing this because it minimizes the energy. What will happen then is, let me put the electrons in here. So these guys are just still sitting there on the first floor. But now I had 2 in the S room and 2 in the P room, and now they can all be in the same room together, and they can each have their own orbital, their own bed. The shape of these orbitals allows for better overlap with the orbitals of another atom, and that lowers the energy. So that's what's driving it. So what would that look like? Well, here's an S orbital, spherical, and here are the 3 P orbitals. So when we combine these 4 things, we have to end up with 4 orbitals. So thankfully we don't have to deal with the math of how do you average this and this, right? Well, you get something that looks like that. And this one, and this one, and this one. You get 4 things that are equivalent in shape, and they're going to be spaced equally in 3 dimensions, right? So we're going to get 4 orbitals. These are now lopsided, because when this overlaps with this, we're going to get one of these lobes is bigger and one is smaller. This little lobe over here, we're mostly going to ignore, because if we try to draw all 3 of these together, it gets really messy. So this picture is just looking at the larger lobes. I like how they use the colors here, blue and red, and you mix them and you get purple, right? So these are combination. 4 orbitals. These are called sp3 orbitals because it's an s orbital and 3 p orbitals, sp3. 4 things arrange themselves in a tetrahedron, right? So we've taken these guys are going off in different directions, and then there's this s orbital. We've combined them together to make 4 equivalent orbitals. Well, this is the rooms got remodeled. I broke down the wall between the S room and the P room. So now all 4 of those beds are the same price, right? This is the same thing. This is just looking at the pictures. Yeah. So we call this an sp3 hybrid orbital, and this has angles of 109.5 because it's a tetrahedron. So when we look at the orbital diagram here for the hybridized orbitals, we've got 4 sp3 orbitals. So before it looked like this, where we had S and 3 Ps. This is S and this is P. These are the atomic orbitals. When we hybridize, we combine these and make 4 equivalent orbitals. So I'm breaking down the wall between the S room and the P room, remodeling it into one large room, and now these beds all are equivalent. They cost the same amount to stay in. And this is kind of nice because now everybody can have their own bed. So this gives us these 4 half-filled orbitals indicated by the purple balloons here. This half-filled orbital of carbon can overlap with the half-filled s orbital of hydrogen. So here we've got hydrogen. Actually, I'm going to do it this way. No. So there's hydrogen, and these guys can overlap. And here's another hydrogen, and those guys can overlap. And a 4th hydrogen. I'm sorry, that would be a 3rd hydrogen. And these can overlap, and a 4th hydrogen. So we have 4 hydrogens. Yeah, you could say hybridization is like socialism. Yeah. It's making everything equal. Yes? It doesn't have to be hydrogen. These hybrid orbitals could overlap with any half-filled orbital from another atom. Well, helium doesn't have any half-filled orbitals. But fluorine does. Fluorine does, so we could have carbon overlapping with fluorine. Pretty much any atom that's not a noble gas either has half-filled orbitals or by hybridization can be made to have half-filled orbitals. The noble gases, they can do hybridization, but they do it extremely rarely because it usually doesn't help them out at all. No, we're not going to go into extremes. We're going to stay in the middle, just use general stuff. So now the geometry here is tetrahedral, 109.5 degree angles. That agrees with your experimental observations of what methane is. It's CH4, and it has 109.5 degree angles. And the hybrid orbitals make that work. Yes? That's a good question. We will determine whether it's sp3 or sp2 or what combination it is by looking at the Lewis structure and VSEPR theory. And so that's kind of cheating, but it's good enough for Chem 1A, right? You would really know by doing all the calculations and finding out what the lowest energy is. Yeah. But other people have already studied all of this, and so they found that for most things, it matches up really nicely with VSEPR theory. We'll get to that. First, we're going to look at the different combinations, and then we'll look at how do we know which one to use. Any other questions about this? So, what about lone pairs? Well, lone pairs work fine here. If we look at nitrogen, nitrogen has how many valence electrons? 5, right? 1, 2, 3, 4, 5. This is S and this is P. If we hybridize those, we get 4 equivalent sp3 orbitals, and Hund's rule still applies. We're going to fill them separately, 1, 2, 3, 4, before they pair up, and so there's going to be pair in that first one. This predicts that I'm going to have one of these orbitals with a lone pair, and this is half filled, it can overlap with a hydrogen, and this one's half filled, can overlap with a hydrogen, and that one's half filled and can overlap with a hydrogen. Yes? It always overlaps with whatever it's bonding to. We're using hydrogen here because it's easy.
Oh, it's ammonia.
Yeah. Yeah, so this is just ammonia, NH3. And we learned by drawing Lewis structures that nitrogen here has a lone pair on it, and then there's 4 electron groups. It's going to have a tetrahedral electron geometry and a trigonal pyramid molecular geometry. And the hybridization here matches up very nicely with that. The bond angle here is going to be a little less than 109.5 because this unhybridized p orbital, or the sp3 orbital with the lone pair, is going to take up some more space. The way this explains it is the hybridization is not complete because of the lone pair. And so then these orbitals are a little more towards the 90 degrees that the unhybridized p orbitals were. That's a small, fine detail there. So how many sp3 hybrid orbitals result from the hybridization of 1s and 3p orbitals? How many orbitals are we starting with? 4. 1s and 3p. 1 plus 3 is 4, right? If we start with 4 regular orbitals, we end up with 4 hybrid orbitals. Okay? You're going to get 4 sp3s. Because it's 1 orbital. There's only 1 bed in the s room. Yeah, the orbitals are beds, and the electrons are the people in the beds. And you see why I like my hotel analogy? Yeah, it works. At first I didn't realize how valence bond theory worked with it, and then I realized, oh, we're just remodeling the hotel rooms. Awesome. Any other questions? Yeah.
Why are the orbitals merging necessarily and sitting at this lower energy state? Is it because it would take less energy to bond?
The orbitals are going to hybridize because when they do that, they can overlap better with half-filled orbitals on other atoms. And so then that brings the whole energy of this molecule down. Whereas if they don't hybridize, they could still overlap, but it's going to be at a higher energy. So by rearranging, by hybridizing, you have to make an investment to remodel these hotel rooms, but then you get a payoff in, I don't know exactly how, I haven't gone that far into the analogy, but you get a payoff. So the bonds that form are the payoff, and you end up getting money back. It's a good investment. That's why they do it. So we can make an sp2 hybridization. So here we've got the 2s orbital, and this time we're just going to hybridize with 2 of the p orbitals, and we're not going to worry about why yet. So we combine these together, and we get 3 sp2 hybrid orbitals. They're called sp2 because it's an s and 2 p's. And this p orbital that's not hybridized, just sitting there, stays the same. So if we think about the hotel, at the S room, and here's the P room, what we're going to do is we're going to break down this wall, and we're going to put the wall over here. So now we've got these guys and one over here. So this is P, and these are sp2. That's S, and these are P. And we're not going to worry about why we might want to do that. We're just going to go with it. So now we've got 3 sp2 orbitals and this 1 p orbital that's left. There's an s, there's the s orbital, and 2 of the p orbitals. And when these hybridize, we still get these lopsided dumbbell things. It looks more like a turkey drumstick now. There's going to be 3 of them, and they're going to be spread equally in space, which is going to make a trigonal planar shape, right? So this is going to be trigonal, and it's going to have 120-degree angles. And then the p orbital, the unhybridized p orbital, is going to be sticking straight up here, in and out of the screen, because it was the x and the y that hybridized, and so it's the z that's left sticking out. This explains the formation of double bonds. So H2CO has sp2 hybrid orbitals because I'm telling you it does. So here's our carbon, and it hybridizes to form sp2 orbitals and then this leftover p orbital. So we can spread these 4 electrons out, 1 in each. Now, yes, this p orbital is a little higher in energy, but again, there's going to be a payback later, so we're going to be okay with it. Yes?
So for non-SU, you can tell us if it's sp2 or sp3, and that's how we're going to know.
I'm going to show you how you can tell from the Lewis structure. So here's our carbon. That's the central atom. And the oxygens and the hydrogens and the oxygen are terminal atoms, and so we're going to assume that they do not hybridize. Makes everything simpler. So, how to draw this? Well, first of all, I'm going to get rid of this. It's in the way. And I need another hydrogen, because there's 2 hydrogens here. So there's a hydrogen. I'm going to let the electron be black. I don't care. So each of these hydrogens has a half-filled orbital. And so those can overlap with one of these hybrid orbitals on the carbon. And then this oxygen has 2 half-filled orbitals. One of those will overlap with the hybrid orbital, and the other one will overlap with the half-filled p orbital that's not hybridized. And this is what it would look like. So here in the purple, those are the sp2 hybrid orbitals on the carbon. And this is the unhybridized. This is the unhybridized p orbital. So these hybrid orbitals, this one will overlap with the hydrogen, this one will overlap with the hydrogen, this one's going to overlap with one of those half-filled orbitals on the oxygen. Everybody okay with that? Those are end-to-end orbitals, overlaps. And then, see, the oxygen also has a half-filled p orbital. And so these are both sticking up. They're parallel to each other. This one's got 1 electron. This one's got 1 electron. And so they kind of bend towards each other a little bit, and they overlap side to side. So kind of above and below this overlap. Stunned silence. Yeah, my pointer won't work here. So here we have this p orbital on oxygen overlapping with one of the hybrid orbitals here, and the other p orbital overlapping with this unhybridized p orbital. And each of these overlaps with a hydrogen.
How do we get to that drawing? Why is it drawn? Why is it drawn with sp2? Like,
Why is it drawn like this?
No, just the other orbital diagram.
Whoops. Why did I choose sp2 instead of sp3?
No, like, why does sp2 look that way? I missed that.
Oh, because I took the S room and 2 of the P rooms and combined them into 1 room. And then there's a wall now over here, and that's a separate room. So I took down the wall between the S and the P room, and the two beds that were closer over here became part of that big room, but then I erected a wall here, so there's still one that's just a P.
So do you only hybridize when there isn't an electron in that group? Or like how percentage it to
I only hybridized carbon because we are pretending that the others don't hybridize to make things simpler.
Oh, this is simple.
This is simpler, yes. Yeah. So actually, yes, that oxygen would be hybridizing as well, but we're going to ignore it. Hydrogen doesn't hybridize because it can't. Yep.
So, calling this hybridization, when I think of hybridization, I think of making one room, but this is a different kind of hybridization?
No, this is making one room. It's got 3 beds in it instead of 4.
But then the other one goes, the P goes up to.
The P room just stayed.
So what do we erect? Or why is it 2p2? It's just weird. Or sorry, sp2 and that one. It's just.
So
I guess. I mean, I know you said so. Like, it's just.
So we draw these with a space between them, right? But really that's a wall, right? And then these are individual, so maybe we just need to have bold lines for the walls, and then these are the individual beds. So this hybridization, we're breaking down that wall and we're building it over here instead. This bed didn't go anywhere. It was at the end of the room, and we're just moving the wall over.
Right, but how do you know when you do that one versus you just making one whole?
I will explain that later.
Okay.
Yeah. Yes.
So if we were to hybridize oxygen,
I'm not going to answer that because we're not going to. Yeah. We don't want to know. No.
so you run gases to hybridize.
We are only hybridizing the central atoms.
Oh,
That's it. Only the central atom. If you go into like PChem or something, they might do more of this. But in OChem, the central atom's good enough. Yeah. PChem is physical chemistry. Has a lot of math. Yeah. Differential equations and lots of quantum mechanics and thermochemistry. Yeah.
so how did you get from the orbital diagram to the drawing?
That's a good question. How did I get from the orbital diagram to the drawing? So I got this orbital diagram. That comes from this. So when I take the S, come on pointer, the S and the 2p orbitals, and I hybridize these and make 3 equivalent orbitals, I get these purple things. I'm ignoring this little bit here, and these are going to be arranged like this in a triangle. This is what an unhybridized p orbital would look like. So then when I go over here, these are those sp2 hybrid orbitals, the purple balloons. And here's my hydrogen, which is just an s orbital, so that's that blue, overlaps here. And here's the oxygen. The oxygen has 2 half-filled p orbitals that aren't hybridized. So here's one of them, and that can overlap end to end with this one. And then the other one's sticking up. The full one is in and out. And we're not drawing it because that would make this more complicated than it already is, right? We have a half-filled unhybridized orbital on the carbon and a half-filled unhybridized orbital on the oxygen, and those can overlap side to side. It's a different kind of a bond. But now we have 2 bonds. We have this bond and this bond. And this bond might look like 2 bonds, but it's one bond because of the wave particle thing, and it's a standing wave with a bit up here and a bit down there. Yes. Yes.
How do you know which ones from O, the overlap of the one
How do I know which orbitals from oxygen will overlap with the carbon? The half-filled ones. So here, oxygen has a full 2s orbital and a full 2p orbital, and we didn't draw either of those in the balloon picture. And it has a half-filled 2p orbital and another half-filled 2p orbital. So these half-filled orbitals can overlap with the orbitals over here. This one overlaps with the hybrid orbital, and the other one overlaps with the p orbital because of geometry. This orbital is at right angles to this one. This orbital cannot overlap with one of those, right? Because those are on the other side.
Yeah, it's more accessible to the p orbital.
Yeah. So this can overlap very nicely with one of the p orbitals. The other p orbital is perpendicular, but the carbon also has a perpendicular unhybridized p orbital, and these can overlap side to side with each other. The overlap there is not as good, but it's still better than not. Yes?
Are we just supposed to recognize this or also draw it?
I'm not going to make you draw these. Yeah. You don't have to draw them. You should be able to picture them in your head, but that's a lot easier than actually drawing them. They're just a real pain to draw. I will attempt to draw some of them later in this lecture, but yeah, you can laugh at me. It's fine. This end-to-end overlap is called a sigma bond. And this side-to-side overlap is called a pi bond. Okay? So the sigma bond, if I look at the letter sigma, it's like a circle with a little tail at the top. If I imagine standing here at the oxygen nucleus and looking down this axis to the carbon nucleus, what would this bond look like? Look like a circle, right? Sigma bonds are spherical. They're end-to-end overlap. This bond is not, and so this is a pi bond. This is not why it's called a pi bond, but it kind of looks like a pi if you turn your head sideways. Okay? So there's two kinds of bonds. There's sigma bonds and pi bonds. The pi bond is when you have a side-to-side overlap. So here's the half-filled p orbital maybe on the carbon and a half-filled p orbital on the oxygen, and they can overlap side to side. The overlap is not as good. These half-filled p orbitals can overlap end to end, and you get a sigma bond. This is better overlap. But so you make one of these, and then if you want to make more bonds there, they have to be this kind. Because this one can't overlap any other, they can't do end-to-end overlap with anything. So pi bond, side-to-side overlap of p orbitals, and it's always the unhybridized. Pi bond is p orbitals. The sigma bond, it is the end-to-end overlap. That could be s orbitals or hybrid orbitals. It could be p orbitals, anything. This is that same molecule. Okay, same molecule. Here's the Lewis structure. We look at the Lewis structure. We've got a single bond with carbon, a single bond with hydrogen, and a double bond with oxygen. So here are our sp2 hybrid orbitals. They're making a bond with hydrogen, a bond with the other hydrogen, and a sigma bond with oxygen. And then the double bond is the unhybridized p orbitals overlapping side to side. So the first bond is a sigma bond. The second is a pi bond. So sigma and then pi. And here these single bonds are always sigma bonds. Yeah, it could be upside down, twisted around, yeah. So we can label the bonds, and you'll need to do this on the worksheet. So the bonds are labeled like this. We first indicate what kind of a bond, what's the overlap. Is it side to side? It's a pi bond. Is it end to end? It's a sigma bond. So we specify the type of bond, and then there's a colon, and then we indicate the two atoms that are participating in the bond. Here we've got carbon and oxygen, and then in parentheses we tell what kind of orbital they're contributing here. So here it's the carbon is having a half-filled p orbital, and the oxygen has a half-filled p orbital. The pi bonds are always going to be p orbitals, always. This one is these two actually. Sigma bond between carbon and hydrogen. The carbon is using an sp2 hybrid orbital, and the hydrogen is using an s orbital. In this bond, the carbon's using an sp2 and the hydrogen's using an s. And then this bond is between carbon and oxygen. The carbon is using an sp2 hybrid and the oxygen's using a p. Yeah, I'm going to get some examples. So valence bond theory gives us more insight than the Lewis model does. Is now we see that double bond between carbon and oxygen actually has two different kinds of bonds. It's got the sigma bond, the end-to-end overlap, and then that side-to-side pi bond overlap. Whenever we see a double bond in a Lewis structure, it always corresponds to a sigma and a pi bond in valence bond theory. So looking at this Lewis structure, I know that one of those is a sigma bond and one's a pi bond. You can't have two sigma bonds. You can't have just two pi bonds. Double bond is a sigma and a pi. In general, those pi bonds are weaker because they don't overlap as well, right? It's like they're kind of leaning sideways to overlap instead of coming head on. So the sigma bonds are stronger. And we observe in real life that the pi bond is easier to break than the sigma bond. So you can break one of the bonds and not the other, and that's an important idea for OCHEM. Another thing that this explains is rotation of bonds. So this is the molecule here. We have two carbons, and so we're doing sp3 hybridization on these, and they're forming sigma bonds, each with two hydrogens and a chlorine, and then the other carbon. So we have this one sigma bond in the middle. Over here, slightly different molecule with a double bond. Here, the bond between the carbons is a single bond, sigma, and a pi bond. So enter model kits. Of course, this is not. Should have set this up beforehand, but I didn't. That's not good. So in a single bond, we can have free rotation, and in a double bond, we can't. Here's illustrations of space-filling models. So here, same two molecules we're looking at. Here, free rotation. So this, we could have the chlorines on kind of opposite sides of the molecule or on the same side. It can spin around, and it does. Over here with the double bond, though, we have to pick one. We can have the two chlorines on one side of the double bond, or we can have one chlorine on one side and one chlorine on the other side. And these are actually two different molecules. They have slightly different chemical properties. They have the same formula and the same molar mass, but their properties are a little bit different. This one's called cis 1,2-dichloroethane, because these two are on the same side, like sisters hopefully would be on the same side if they were having a fight with someone. I don't This is called trans because they're on opposite sides. Like the transatlantic means you're going across the Atlantic Ocean, right? Trans means across. So here these are across. Any questions? And again, this is an important idea for OChem. This slide has so many words on it. So we learned that double bonds are stronger and shorter than single bonds. And the example here is a carbon-carbon single bond has a bond energy of 347. A carbon-carbon double bond has a bond energy of 611. It's more, right? According to valence bond theory, why is a double bond not simply twice as strong as a single bond? Because 349 times 2 is more than 611, right? It'd be 694. So why isn't this twice as strong? 3 choices. Because according to valence bond theory, a double bond is actually composed of 2 different kinds of bonds, one sigma and one pi. A double bond is the sharing of 2 electron pairs, or this is an exception. According to valence bond theory, a double bond is generally twice as strong as a single bond. It's A. It's not twice as strong because the second bond is a different kind of bond and it's weaker. So combined, those 2 bonds are stronger than a single bond, but they are not twice as strong. Any question? So let's look at another combination. One of the s orbital and only one of the p orbitals. And again, we're going to explain when you would do this later. So that's going to form 2 orbitals, hybrid orbitals sp, and it's going to leave 2 unhybridized p orbitals. Again, in the hotel, we're just moving the wall over to include 1 more bed, and we're going to leave the other 2 beds in the p room. We're not going to think about why yet. So here we have the s orbital and the p orbital. It's a little easier to see how when you combine those, you could end up with these 2 things. Again, we're ignoring the small lobe, and we're just looking at the big ones. So this is showing the 2 hybrid orbitals together. They're perpendicular. I'm sorry, they're arranged in a line, and this was using the px orbital, and so the py orbital and the pz orbital are sticking out at right angles to this. Just kind of a silly thing. Draw the Lewis structure for acetylene. Well, it's really similar to that formula. We'll go through all the steps and we'll end up with that. Acetylene has an sp hybrid orbital. So here we're going to hybridize the carbon, form two sp hybrid orbitals and 2 unhybridized orbitals. We have 2 carbons here. We have 2 central atoms. The central atoms are hybridized. Yeah, thank you. So here's 1 carbon, here's another carbon. The sp hybrid orbital can overlap. I'm going to bring the hydrogens over here. This is hydrogen, and this is hydrogen. So we can get an overlap between the hybrid orbital oops, I did that wrong. I meant to have it over here. So here's the S of the hydrogen, and that can overlap with one of the hybrid orbitals of that carbon. And our other hydrogen can overlap, I put that one in the wrong place too. Can overlap with a hybrid orbital of that carbon. And then this hybrid orbital and that hybrid orbital for the carbons can overlap. And those are all going to form sigma bonds. And then these guys, the unhybridized p orbitals, can overlap and form pi bonds. Isn't that a mess? Kind of looks like a really fun pool float or something. Here's the carbon. This is an sp hybrid orbital and the other sp hybrid orbital. One of them is overlapping with hydrogen. The other is overlapping with an sp hybrid orbital of the other carbon. And it's got this hybrid over here that's overlapping with the hydrogen. Then it has two half-filled p orbitals, one going up and down on each carbon, and those will overlap side to side. And one going in and out on each carbon, and those are going to overlap side to side. And so we get a triple bond. A triple bond is 1 sigma and 2 pi bonds. There are 3 colors because blue and red represent unhybridized orbitals, and purple represents a combination of blue and red. It's a hybrid orbital. These hybrid orbitals are linear, and the molecule is going to be linear, and that agrees with Vesper theory and experiment. And so we can see the labeling here. We've got a sigma between sp and sp on the 2 carbons. These are pi bonds between p orbitals on each carbon. This is a sigma between the sp hybrid on the carbon and the regular s on the hydrogen.
So I thought all of them were hybrids.
So they're not all hybrids. When we do this hybridization, well, actually, let's maybe go back to this one. So here we're taking one of the 2 p orbitals and the s orbital. We're hybridizing those. Those are the hybrid, and those we're leaving alone, not changed. And again, I haven't explained to you how do we know how many to do. We'll get to that still. So we can hybridize the s in 3 p's, or the s in 2 p, or the s in 1 p. You can't hybridize 2 p orbitals with each other because it's not going to do anything. Does that help? No? What is the hybridization of carbon in CO2? But you didn't tell us how to do this. Well, let's look at the Lewis structure for CO2. Here's the Lewis structure for CO2. We've got a double bond between the carbon and the hydrogen. A double bond is always 1 sigma bond and 1 pi bond, right? And here's another double bond. We've got a sigma bond and a pi bond. So the carbon is going to form 2 sigma bonds and 2 pi bonds. The pi bonds have to be unhybridized p orbitals because those are the ones that stick out and can overlap side to side. And we need 2 hybrid orbitals to make the sigma bonds. So what's the combination? SP. This is SP. So carbon has 4 valence electrons. So this, if we look at 1 carbon, if it makes an sp hybrid, that's going to have 2 lobes, and then two unhybridized p orbitals. There's going to be one sticking up and one down, and one going back and one sticking out. Three-dimensional. These are the ones that can overlap side to side with the oxygen to form the pi bond. And these are the ones that can form the sigma bond.
So how do we determine which are hybridized by looking at?
Well,
Or how did you determine this?
yeah, how did I do this? Well, from the Lewis structure, I see that I have two double bonds.
Right.
A double bond is always a sigma bond and a pi bond. Pi bonds are never hybridized. They're always regular p orbitals. Pi bonds, p orbitals, period. So if I have two pi bonds, that means I must have two unhybridized p orbitals. Okay? Pi bonds are always unhybridized p orbitals. Always. Not hybridized. So the way we do this, other than thinking through it like this, is we're going to look at how many electron groups are on the central atom. How many electron groups on this carbon? 2, right? A double bond counts as a group in Vesper theory. 2 groups, that means I need 2 hybrid orbitals. So I'm going to take an S and a P. Well, on the carbon, I need 2 unhybridized p orbitals, 1 each for those pi bonds. Correct. These are not hybridized. This is hybridized. It came from, I didn't mean to do this in red, but there it is in red. So this is regular carbon, right? And what I'm doing here is I'm going to combine these two into one orbital, one room. And so that's this part right here.
Yeah, but would there be 3?
Yeah.
3 electrons?
Yeah.
These are very close in energy. They're closer in energy now, and so this electron says I'm gonna go up here and get my own bed. They're gonna spread out, and half fill as many as possible. I know, this is painful, isn't it? You guys are asking really good questions though, so this is awesome. Okay, so you saw me writing on my hand. So I'm going to look at the central atom and ask myself how many electron groups. So 2, 1, 2, sp, hybridization. If there are 3 groups, 1, 2, 3, sp2. If there's 4, sp3. So if I need 2 groups, I'm going to take the s orbital and 1 of the p's. If I need 3, the s and 2 of the p's. And if I need 4, the s and 3 p's. Because these are my orbitals, and so I have to start with the s, and then I'm going to pull in however many other ones I need. The electron groups, this double bond has a sigma bond, right? The sigma bond is going to be made with the hybrid orbitals. The pi bond, the second part, is going to be made with a p orbital. And so with this electron group, I need 1 hybrid orbital for the electron group, for this double bond. Because it's going to use 1 of these, and then the second bond is going to be a pi bond with these unhybridized orbitals. Mm-hmm. This is 1 orbital, and this is another orbital.
I was putting them together as pairs, right? Because it's S orbital and then it's two orbitals.
So there's another little lobe. This is actually two orbitals going opposite directions. This is one orbital, and this is one orbital. So there are 4 orbitals there. We're used to seeing something like this and saying, oh, well, that's a p orbital, is one thing. This is actually 2 things. But the little nub here, we don't draw. I took 2 and combined them, an S and a P, and so it's an SP. Let's keep going and see if maybe some things will clear up. Well, that gets into d orbitals. That might not be good. Let's look at this one again. So this is the sp2. I'm sorry, the sp hybridization. So on the carbon, this is one sp orbital, and this is the other sp orbital. And this is up and down is one p orbital, and back and forth is one p orbital. So carbon has 4 half-filled orbitals. In this structure, if I look at this carbon, how many electron groups are on that carbon? 2. For Vesper theory, 4 electron groups, not pairs, electron groups. Double bond counts as one group. Single bond counts as one group. So two groups, sp hybridization. So here's one sp, and here's the other sp, and then I have 2 unhybridized pi bonds. So this is unhybridized carbon. And then it's going to hybridize like this. And then the difference in energy between these levels is small enough that they can each have their own bed. And I get 4 half-filled orbitals. This one overlaps with a hydrogen. This one overlaps with the other carbon. And then these p orbitals do a side-to-side overlap with the unhybridized p orbitals on the other carbon.
How come it's only 2 groups for both? Because you know for SPDF it's 1.57. How come it's just 2? I don't think it's.
Well, the S room has 1 bed, the P room has 3 beds.
It's just 1.
So I started out with 4 beds, and I still have 4 beds. I just changed what rooms they're in. I remodeled the rooms. So I made this, I took the wall down here and incorporated one of the P beds into my S room. And so I can't call it an S room or a P room because it's neither, it's kind of both. So I'm going to call it an SP room. And then this is the 2 that got left alone. But now this P room only has 2 beds in it. There's 2 orbitals. Each orbital is a bed. Well, on one atom there's, oh, you mean the 2s orbital, 2s electrons?
Yeah.
This, when I hybridize these, now the difference in price between these 2 hotel rooms gets smaller. And so this cheap electron here that didn't want to pay for the P room, his SP room is more expensive now, and so going up to the P room to have his own bed is worth it. It's like an extra $1 a night or something. He's like, yeah, well, yeah. I'm not going to pay $20 a night to have my own bed, but I will pay $1. And so he'll move up.
So one of the S's just moves up to the P goes down to an S.
This P gets hybridized, combined, mashed together, and these 2 get left out. See, usually I lecture on this, and people just sit there and stare at me, and I know they're not getting it, but they don't ask me questions. So this is awesome. You're asking questions. It's taking forever, but you're asking questions. So that's great. So you have a question, ask away. Right. So what you're saying is you put these two together. Oops, that's not what I meant to do. You put these two together. What? Oh. Those two together, and there were 3 electrons there. And so now, why are there only 2 electrons in this one? Because this guy said, well, let's do it like this. So this is immediately after hybridization. This is what you want it to look like, right? Because you took those and you hybridized, and there's 3 electrons in there. I think you're on the same boat, right? The energy difference here is very small, and so this electron's saying, I don't like sleeping with this guy. I could pay just a little bit extra and move over here. And electrons can move, they can switch beds, they can switch orbitals.
And then it's the rule, right, that each one has to have.
They have to have parallel spins. So when this electron comes over here, he's not going to stay upside down in the bed, because the first one always goes in right side up. It was in the S subshell. It was in an S orbital. But it's just an electron. And if it moves to a p orbital, then it's a p electron. Because electrons are the same, it's just where are they staying.
I thought hybridization would be like the electrons would, and one would flip upside down so that they had opposite spins and kind of like naturally with each other. So now they're not doing that. So.
No, hybridization does not have to do with spin pairing. Hybridization has to do with combining 2 orbitals that are different to make multiple orbitals that are the same.
Yeah, because earlier in the chapter it said that it like overlapped, and now they're not. Like I don't get it.
Well, the overlap is here, is right here, where this one is overlapping with the orbital from another atom. They're each half-filled, and when the 2 half-filled orbitals overlap, one from each atom, the electrons spin pair, and that causes a lowering in energy. So this is the sp electron, this is a hybrid orbital from one carbon overlapping with the hybrid orbital from another carbon. So the overlap is not within an atom, it's between 2 different atoms. Does that help? Yeah.
So with the double bond, we have a pi and a sigma,
Mm-hmm.
right? And a pi, we can only have 1 pi.
No, you can have 2 pi bonds,
You have 2 pi, then.
but you have to have a sigma first.
Okay, so if we had
You can have a sigma and 2 pi's, which is what we've got here.
we have
I have a pumpkin pie sitting at home.
I thought we only had.
Instead of doing carbon dioxide,
we have-
we do with another one.
Well, we have
Yeah,
two,
we could.
We have 2 pi's, but it's just 1. All right.
There are two p orbitals. This is a p orbital, and this is a p orbital. And when they overlap, they form one bond.
And that's the pi.
That's a pi bond. But then there's a second p orbital here, and those overlap and form a second pi bond. There's 2 pi bonds and a sigma bond. This is a triple bond here.
So, I understand now. Because I know within a double, there's 1 and 1, right? So
Yeah.
if you have a triple, now it's 2 to 1. I'm just trying to wrap my head around.
Yeah. Okay. So let's do this. So we got 1 carbon that's got sp hybrid orbitals. Let's maybe draw that. So it started out like this. And it hybridized and did this. Mostly just because. That's P and this is SP. And so this is one of the sp hybrid orbitals, and it's got an electron in it. And this is the other sp orbital, and it has an electron in it. Okay? That's these guys. Purple. And then I have two unhybridized p orbitals. So there's this guy up here, and that's one orbital. And the other one's perpendicular, is kind of sticking out and sticking back. It's three-dimensional, not very pretty, sorry. So this has an electron, and this one has an electron.
Also, each P counts as pi.
Each p orbital makes a pi bond. So I have two p orbitals, I can make two pi bonds. So that's the one atom. And then the other atom is like it. It also has an sp hybrid and an sp hybrid. The electron, it was right side up. It's going to flip and pair. And it has an electron over here. Question?
Why does the sp, so that's one orbital and it has two electrons in it major, right?
This is two orbitals.
S and P.
No, it's one sp on this side and another sp on the other side. These are not like a p orbital where both, this has two lobes, one on each side, but they're part of the same orbital.
Okay, I get it.
Okay? Because the sp orbital actually has this, it does have two lobes, but the other lobe is really small. And because they form this shape and then they overlap weird, it's icky to draw those. Yeah.
This is per carbon. So, or like this, but say it was a nitrogen, and it was instead of 4 electrons, it was 5 electrons. What are we looking in the sp one going down?
Well, let's not worry about that just yet. Let's try to understand this one first. And then this one also has an unhybridized p orbital in the z or y direction or whatever that is. And this one like that. And these will switch their spin so that they can pair up. And then they're going to bond side to side. So here's my sigma bond between the two sp orbitals, one on this one and one on that one. And then there's a p orbital here and a p orbital here, and they together make one bond, a pi bond. And here's the other p orbital on each, and those overlap side to side, and they make one pi bond. There's this other sp orbital here that's half filled, and that's going to overlap with something else. In our example here, it was the hydrogen.
It's the P orbitals that are coming out.
The p orbitals are messing you up.
How is there? So we have. Why is
Why are there 4 p orbitals?
am I saying that wrong?
No.
Is there 4? Is there 2?
Well, there's 2 on each atom. So we have another carbon atom over here.
So for every SP, there's 2. Okay, I get that. All right.
This really was harder than
Oh no, I just.
Well, you guys are really trying to understand it.
So okay, so for every SP, there's 2 P's. So in this case, we have 2 SPs, right? Or we have 2 SP orbitals.
We have 2 sp orbitals, and then what's left is 2 individual p orbitals.
For every
Yeah.
SP orbital. Okay.
Because you start with 4 orbitals. And so if you hybridize 2, then you have 2 left. So carbon's going to have 4 orbitals. We can make 4 sp3 orbitals, or we can make 3 sp2 orbitals and 1 p left over, or we can do s and p and have 2 left over. The combination, you still have to have 4 orbitals for carbon. So these guys, well, maybe do the purple. I don't know. We're going to get an overlap between these two for that sigma bond. And then we're going to get overlap between a P and a P and the other P and the other P. So we got half-filled things overlapping. Yes? Where do these come from? Okay, so we started out with S and P, right? So when we started out, we had 1 s orbital and 3 p orbitals. And when we hybridized, we took one of these p orbitals to hybridize with the s, and that's where we got these guys, sp, hybrid. And what was left was these 2 p orbitals that we didn't do anything to, and so they're just going to sit there as p orbitals. The electron from the s, what used to be the s orbital, moved over here because the energy difference was only a little bit, and it would really prefer to have its own orbital. Does that help? Why isn't this an SP as well? Because where the electrons come from has nothing to do with the shape of the orbitals. So if we're talking about the hotel, right, and I had the S room had 1 bed in it and there were 2 people staying there, and then I had the P room with 3 beds and there were 2 people staying there, and they went out for lunch and we remodeled the room. So I broke this wall down and moved the wall over, and so now there are 2 beds in this room and 2 beds in the other room, so 2 and 2. And then they come back, and it's like, well, that was my bed, this is my bed, this was my bed. And then the guy that was sleeping here, it's like, it's only $10 a night extra to go to the next room and have my own bed. I'm going to move over there. This electron had nothing to do with the remodeling of the room. So where the electron originally was doesn't matter. They can stay anywhere. And then if you zap them with electricity, they can jump up to higher floors. I mean, they just go all over the place. Does that help? A little bit? We would like the orbitals to be full, because if the orbitals are full, then we have an octet, right? Well, because when they spread out like this, they can overlap with half-filled orbitals on another atom, and then everybody can be full. So maybe these are male electrons, and the electrons from the other atom are female electrons. I don't know. They're getting together, and love is in the air or something. I don't know. Well, you want to look at carbon dioxide again? A different one? Mm-hmm. Well, so this is 1 orbital, not 2. And this is 1 orbital. And that is confusing. So there are the 2, well, let's do it this way. So here's a p orbital, and this is a p orbital, and this is an sp orbital, and this is an sp orbital. We're not showing this little bit because it gets confusing. when we put them together. So the hybrid orbitals, we're just looking at one lobe. The unhybridized p orbitals, both lobes are part of the same orbital. And so it looks like, yeah, there's 4 red balloons there, but it's only 2 orbitals. But these go on both sides of the atom. That orbital does. It's a lot to get your mind around. And I wish I could, like make beautiful pictures instead of these ugly things.
So like half of the side is half energy, and you draw the other side to get full energy with the orbitals and all that.
Sort of, yeah. So what happens here is this carbon atom is arranging itself so it can have maximum overlap with this other carbon atom. And so they both have sp hybrids, and they both have unhybridized p orbitals, and so they can overlap and they can make 3 bonds with each other. They can't do 4, but they can do 3, and that's the most they can do. And we use Vesper theory to predict how many hybrid orbitals they're going to make based on the number of groups, because every single bond is a sigma bond, and if you have a multiple bond, it's a sigma bond plus a pi bond. And a lone pair would be a hybrid orbital too. And so the number of electron groups corresponds to the number of hybrid orbitals that you need. So you want another example. Let me just move ahead and see if there's well, this one might work. HCN. So we need the Lewis structure. We've done this one before. Here we have H, C, and then nitrogen on the end here. And so we're looking at this carbon atom, and we're asking ourselves how many groups of electrons? 2 groups, right? So what's the hybridization? sp. So this is sp hybridization. The single bond is a group, and the triple bond is a group. No, groups don't equal bonds. But so 2 groups, well, 2 electron groups, and that's what we learned in Vesper theory. So we need 2 hybrid orbitals. So if we're looking at our original orbital diagram for carbon would look like this. We need 2 hybrid orbitals, and so we're going to take S and P, because we need 2 orbitals to make 2 orbitals. We hybridize these, and then they become closer in energy, and so this electron decides to move up and get its own bed in this other room. So I've got SP, I have 2 sp orbitals, and I have 2 unhybridized p orbitals. So that's what the carbon is doing. The hydrogen and the nitrogen, we're not going to hybridize them at all. So here's the hydrogen. And then the nitrogen, because they're not central. So this is the orbital diagram for nitrogen, right? So the carbon here is going to overlap and make a sigma bond. a sigma bond with the hydrogen. So that's this one right here. And this is a lone pair. And it's going to overlap there. And that's going to form one of these. It's too skinny before, now it's too fat. No, I did that wrong. Sorry.
Oh, because it's bonded once with the orbital, once with the hydrogen.
Yeah, one of these overlaps with the hydrogen to make the bond on this side, and the other one overlaps with nitrogen to make a bond on this side.
And so all those things.
And then I have 2 unhybridized p orbitals and 2 unhybridized p orbitals, and those can overlap and form pi bonds. And that's the second and third bond. So here's my carbon. It's got an sp orbital over there and an sp orbital over here. And it's got an electron in each. And it has an unhybridized orbital, p orbital, going up and down, and the other one's going in and out of the screen, and those are also having an electron in them. So this is one orbital, this is another orbital, this is a third one, and a fourth. We have 4 orbitals, they each have 1 electron, and that's what this is trying to represent. Then I've got my my hydrogen over here. There's my hydrogen. It just has an s orbital, and its electron will flip. So the electron here, when it overlaps with this one, that one's going to flip over, and they're going to pair up like this. And then the nitrogen over here, so the nitrogen has a lone pair in an s orbital, and then it has 3 p orbitals. It's got one going this way, and one going up and down, and one going in and out. Burgers. So I've got this one is overlapping with this, it's making a sigma bond. So there's the electron from the nitrogen. And then these guys are overlapping. And then these guys are overlapping. And so I have 2 pi bonds, this one and that one, 2 slightly different shades of red, and then I have 1 sigma bond. And what this is asking, it says it wants a bonding scheme, and so it wants us to label those bonds. And so if I'm labeling these these pi bonds, I have 2 pi bonds. They are between carbon and nitrogen. And on the carbon, I'm using a p orbital, and on the nitrogen, I'm using a p orbital. And so that describes both of those. They have the same description. And yeah.
Would you find a way indicating that there's 2 of those bonds?
That's a good question. Would you indicate that there's 2? We don't usually, although, here I'm kind of indicating it by pointing out that it's this bond and that bond. I suppose that you could designate that this is PY and PY, and then you could do the other one as PZ and PZ. But we usually don't go that far. And then I have sigma bonds. So this one in here is between carbon and nitrogen. And so this is this purple SP for carbon, and what's overlapping on the nitrogen is a P. And then I have another one, whoops, between carbon and hydrogen for this guy right here. And that's SP and S on hydrogen. Is there another way to get the bonding scheme other than drawing it out like this? Yes. You don't actually have to draw the picture. You can look at the orbital diagrams. But you kind of have to be able to visualize at least a little bit what the little boxes are representing. So here I've got, with the nitrogen and the carbon, you see I have three things overlapping. One of those, the first one has to be a sigma bond, an end-to-end. And usually that's going to be the hybrid orbital on the central atom, and then these we're pretending are unhybridized. And the second and third bond are going to be between p orbitals on both. And those are going to be the pi bonds. And here I have one bond. It's between carbon SP and hydrogen S. And it's the first bond between them, and it's going to be sigma. This is sigma, carbon SP, nitrogen P. And these two are both pi, carbon P and nitrogen P. This one over here, that's this guy right here. It's between an SP hybrid orbital on the carbon and an S orbital on the hydrogen. It's a sigma bond. It's kind of hard to think of, well, how do you overlap with the end of an S orbital, but it's the end of the SP orbital